we're just going to go about our usual routine. Some introductions, since we don't have anyone new, so no introductions. So we'll just go about like sharing some work updates, if any, and then we'll have a presentation which is on cost compression in low-rise multifamily buildings by Joe Rendall from Oak Ridge National Lab. And post that, we'll have some discussion and we'll wrap it up with some closing notes from my side. So with respect to updates, I just wanted to share an update that we had the heat pump water heater day on 23rd October, which was last month. It was a really good, great success. We had some really interesting panels, a lot of panelists, and we had a good number of audience who had joined us right from the morning till the evening. Dipti was also a moderator for one of the panelists. Maggie was a panelist for the Future to Roadmap 2040. And if you have missed it out, you could actually see all the recordings. It's uploaded on the AWHI YouTube page. So you could find all the recordings for all the panel sessions and also the heat from water heater dance in the end, which you should not miss. It was the biggest fun part of the entire event. So definitely give it a watch. Do check out the page and all the sessions out there. So that's all from my side. Dipti, do you want to share any updates?
Nothing much from my side. Yeah, heat pump water heater day was really a great success. It was like drinking from a fire hose actually. Like so many things happening in this world and all at once on one day. It was amazing. Learned a lot and it was a great time to like know each other too. So a lot of LinkedIn updates after that, like my network increased, got
Yeah.
to conversations about heat pump water heaters and domestic water heating in general. So it was a great day, and I'm really looking forward to next year and how else I can have like more NEEP involved in this. So yeah, it was very good.
Yeah. Thank you, Dipti.
Yeah.
Noah, Alicia, Joe, do you have any updates to share, or do you just want to share something related to your work?
I don't have
No.
any. Oh, go ahead.
Oh, all I was gonna say is, yeah, no updates from me. Just wanted to echo, great heat pump water heater day, and yeah, finishing up some conversations on heat pump water heater cost compression. It's not really a study, but more just research and aggregation of different installers' thoughts on the matter. And it's just mainly comprised for single family homes, less on the multifamily side. But yeah, gonna write a kind of fact sheet white paper early next year and probably publish it on AWHI. And that's the funding is coming through PNNL.
Thank you for that, Noah. Alicia, you were saying something?
Yeah, I was saying I don't think I have any updates specific to this as my cat tries to knock over his food. But I kind of separately, but still interesting and important. Some of the things that we're working on at CEC right now. I'm working on actually doing the outreach for our stakeholder outreach and engagement plan, which is heavily equity focused. So I'm really interested in hearing these conversations as it's good for me, who is a little bit new into this space, to understand like the equity concerns that we're talking about as I go into that stakeholder engagement work. So excited to be here and continue to learn.
Thank you, Alicia. Hey, Paul, good to have you on the call. Just in
Hey,
case.
everybody. Yeah,
Okay.
and I was just going to mention, because I told you I'm in a more public place, so I'll be on
Perfect.
listen mode, but I just was going to mention that I was talking to Energy Star Jill Vore earlier. They're very much committed to continuing to drive their message to the low to moderate income customer, and they're going to have a lot of information to share for next year's Earth Day conversation. So just letting you know that that's still a high priority for them, even considering the the anticipated changes in the administration and how the impacts might play out. But they've been preparing for that. So Jill Vore is still very confident that they'll be able to maintain their course, specifically for the lower to moderate income customers. So I'll keep you guys informed.
Thank you for that heads up, Paul. We are keeping our fingers crossed too. Hey, Tabitha, good to have you on the call today.
Hello.
Do you have any work updates that you would like to share with the group, or any just like any random information that you're working on, some project or something?
I think y'all already know everything I work on. Happy to be here.
Yeah, thank you for that, Savita. So we'll just move forward with our presentation today. Joe, do you want me to drive the slides, or do you want to take control and do it yourself, whichever is feasible?
Either works for me.
Yes, totally
Whatever you
fine.
prefer.
Yeah, if you prefer to take like control, that's totally fine. You want me to drive the slides, I can do that for you.
Okay, let me hit the take control button then.
Sounds good.
Okay. So I'm moving these forward for everybody right now, right? So this isn't a new project to everybody, but it's sort of a more extended update of what we've been doing. It's nice to see a lot of the same folks here and maybe some new names that I'm not familiar with, but yeah, so we're going to talk a little bit about equity today and heat pump water heaters, specifically for cold climates. So something we noticed when we were doing a little bit of analysis was that in a cold climate, a unitary heat pump water heater is going to take heat from the space, which requires folks in low to moderate income families to pay for the energy to heat the space, and then the heat pump takes the heat from the space and puts it into your water. So they sort of pay for it twice in some ways, which isn't good for people that have high energy burden. Although in hot climates or moderate climates, a unitary heat pump water heater, especially for single families, is a great solution that maybe has a payback less than 4 years. In really nice climates, maybe even less than that. So what we came up with is what we're now calling the drain source heat pump water heater, which was combining the technology of drain heat recovery with water source heat pump water heaters and a moderate storage tank to make hot water by recovering a new energy stream of what was going down the drain to begin with. This will have the lowest operational costs, and in some places will be cost competitive operational cost wise to natural gas. So we think it's a really interesting solution for folks that have very high energy burden. The two kind of names we're calling it. One is the regenerative braking of water heating. So there's a pretty strong analogy between this configuration and an electric or a hybrid car, and also the not so nice name, or I don't know, it depends how you take it. It's also can be considered poor man's geothermal, because you can essentially harvest heat without having to drill a well. So I got one laugh out of that. So it's a large team, which I'm just part of, looking at a lot of different components of it, experimentation, modeling, and then systems analysis, life cycle cost analysis, and Argon's helping us with CO2 analysis. And I'm lucky enough to be able to share some of those results today from this pretty expansive team. Gary Klein keeps us in check on the water side, and we've had a couple interns also work on the project. We've really helped out well. So I split the problem into 3 technology-based problems and 2 barriers. In a cold climate, the air source heat pump water heater doesn't have great year-round performance. And current sewer heat recovery systems are rather expensive when you combine them with a heat pump. And the operational costs, which I mentioned earlier, typically are higher with heat pumps when you're not maintaining a COP about 3 to 4 to 5, depending on your region and your cost of your energy. And the barrier that used to kind of exist before RA funding, I would say, was the initial costs were an issue for folks of getting heat pump water heaters into their building. But that's sort of been taken away for states that are adopting that. And if you change from a centralized natural gas system to a unitary heat pump water heater, you're going to introduce a new portion of the electrical bill that's going to go to the most likely go to the tenants. So handling that transfer is a little tricky. Some people call it the split incentive problem. Other options out there for switching from centralized systems to unitary heat pump water heaters is either high cost or if you're going to use electric resistance, it's of course going to be high CO2. So we came up with something called the centralized drain source heat pump water heater. You'll see little distributed tanks in this figure here. Those ended up being too expensive when we started to do the cost analysis of the distributed portion of this. Any tank that you put everywhere has to be maintained. And one of the key factors in the financials, just kind of skipping ahead here too, is if you have to replace your unitary heat pump water heater after 15 years, whereas a centralized system you can keep for closer to 30 years, there's a pretty big cost disparity when you do a life cycle cost analysis. So what we're trying to do is reduce costs, increase efficiency, and reduce carbon with this project. Some interesting things that crop up is with the moderate storage tank, you can increase your thermal capacity for load shifting by about 300% because that tank is usually about 3 times larger than your hot water tank. And having this free energy source really increases your COP, especially in the dead middle of winter, is what we're modeling at this point. So if you're using electric resistance backups in the winter for your centralized air source heat pump water heater because the temperature went too low, you could still run your drain heat recovery system, your drain source heat pump water heater at a high efficiency. So that's how we get to the maximum of 400. Is those really cold months and really cold, long, extended cold periods. And the folks over in ORNL helped us out and do reduce the analysis to show that the life cycle carbon will reduce by 75%, which is quite large and pretty notable. So in our background research, we found out that about 50%, a little bit more than 50% of the multifamily units that are 5+ units have centralized systems to begin with. So the market's slightly larger for us to try to approach there and try to fix things there. Also, the apartments that are 5+ unit buildings have a higher energy percentage use in water heating than single family units. So it's a larger portion of their bill. So it's also a very good place to attack. Furthermore, and how we get a little bit more towards the equity portion of it is folks with high energy burden or severe energy burden. Sorry, I haven't updated this. This is supposed to be greater than 10%, are kind of concentrated in these buildings. So it's a real easy place to have high impact quickly to try to focus on multifamily buildings to relieve energy burden. With technologies that reduce your operational costs, thus reducing your energy burden. Are there any questions on this slide before I go forward? Okay, sounds good. I'm kind of preaching to the choir here, so there probably wasn't too much I had to say about that. So in anyways, our project was split into 3 years, component modeling, scaled experimental work, and then going towards a field pilot. And that's what we're looking forward to, is going towards a field pilot in this next year and finishing up the last of our experimental model, our experimental simulation. So we're simulating a 2-unit complex by putting all the piping network together for a centralized system for 2 units that would have been in a 30-unit building. So we're not doing every unit, we're just doing the 2 units. And then we're gonna bring all our hardware, our heat pump water heater, our moderate storage tank, our hot storage tank, all our pumps, recirculation, and see what kind of system performance we get, see if it's matching the model we've put together, because our model is pretty expansive in that I don't want to get ahead of myself yet, but if we validate the model for these cases, we'll be able to do a lot. I'll wait to get to the model slide to talk about the model. Going into before we went to the system model, we looked into components, and this is just one example of a component model that we thought was critical to get right to be able to get good system level results. We looked at the mixing in hot water tanks with CFD, specifically large eddy simulations, which are very intensive for the requirements of your computer. So not a lot of people can do this. So we were working on some of our supercomputers to do the LES modeling, which is models the finer details of what URANs would typically do. So in this region up here, which you can say is about 20% of the capacity of the tank when you're getting rid of it, traditional CFD won't get this as good as the LES will for figuring out what the actual temperatures are in the location. So when you're recharging your hot water tank with a heat pump, say going in a different direct, you pull the water in a different direction. When this water gets to your heat pump, you get really different COPs. So if the thermocline grows too big, which is the region between hot and cold water, if it takes up maybe 50% of your volume, you're going to estimate your COPs wrong because you're not having cold water, you're having warm water going into the heat pump. So there's we haven't finalized the numbers on what the impact will be, but I ballparked them at about 10%. Plus or minus based on how well you're modeling that part. So we went in pretty deep on that one, and we also I'll talk about later is the heat exchangers. But the system model that we did included centralized drain source heat pump water heater configurations. We looked at like 6 or 7 of them. Only one of them turned out to be cost effective compared to the others. We also modeled the central air source heat pump water heater and then some engineering calcs for approximations of unitary air source heat pump water heaters were pulled from some references and compared to experimental data. And then it's pretty simple to model the efficiency of natural gas, central natural gas at 80 or 95%, and then unitary electric resistance water heaters, because they're not very climate dependent on their performance. But what you'll see is in the cold months in Minneapolis, the central air source heat pump water heaters and even the unitary aren't getting a very high COP. Whereas if you have a very constant drain temperature throughout the year, you can still get a high COP because maybe it's 65 Fahrenheit at that time of the year, which is much better than trying to pull heat out of air that's below freezing or near freezing. So it's just an easier thing to do. Yanfei is going to be publishing a paper on this soon. It's just about out the door. We also had to do models and controls. We had to do controls for our models. And we looked at single pass and multi-pass, which are the 2 of the typical configurations people do. Single pass was a little bit more efficient than multi-pass. But you can see the trend here of all the water source systems are relatively constant, but the air source ends up being very dependent on the temperature of the air outside. We also pulled together all the costs for these different component or different systems, a bunch of typical ones, and then the new ones we were suggesting based on first costs through RS means. This was for a 100 person building, so these numbers seem relatively high, but you can sort of whack 2 zeros off if you want to know what the cost is per person for these different technologies. And although the initial costs are quite higher for this drain source heat pump water system in its simplest configuration, the life cycle costs, which will be the next slide, pan out to be best for this system. So you also need to incentivize, the argument we're sort of making is that centralized systems need to be incentivized close to the level of unitary systems to have the lowest life cycle costs. So that's essentially what we did in here. We applied a fictitious incentive for all the centralized systems at the same level of the unitary. When the unitary heat pump water heater, if you're electrifying at the same time through the IRA, there's significant incentives per unit that you're doing. So you'll see that applied here, and then we applied it to our centralized drain source systems and came out with a slightly lower life cycle cost than centralized natural gas at 80% thermal efficiency. And 80% thermal efficiency out in the field is pretty good. So that gave us some confidence in going forward with the rest of the project and the experimental work, because we ended up with the lowest life cycle energy costs. So these are mostly your operational costs. There's some maintenance costs that are also put in the OMRs. And yeah, unitary electric resistance, of course, is the worst. Are there any questions about this slide before I go on? This one's a little bit more involved. One person had new activity. What was that?
Well, even I was trying to see that. I think it doesn't show who has an activity. I just had one question also to this slide and to the one earlier with the energy burden analysis. Um, I'm always curious that energy usage pattern could be slightly subjective in multifamily units. So when you do this whole energy burden analysis, do you also calculate the probability of error that like it could be influenced by because some families might have a really different pattern of using, like for water heating or the water usage, like, we might just have an approximate value. So in that case, how do you calculate the energy burden analysis and then the overall cost, like with respect to the operational cost as well as the life cycle cost?
Okay. Yeah, good question. So there was an input to the model in the system model, which is we take NREL's, and I'm going to forget the name of it, calculator. They have a calculator that randomizes water uses for a single family based on the number of people. Well, the number of bedrooms. The number of people are the number of bedrooms plus one. So we've automated that, and we run it for how many apartments we have it, and then we aggregate that all together. So there's some randomness in it, of course. And that calculator is good for sort of an average family. If you are designing for a senior assisted living, the values probably come down a little bit. So some of those granular things we're thinking about, of course, when we're thinking about going to a pilot and it's going to be an actual field site, how to adjust it up and down a little bit based on additional information we have. But for the comparison viewpoint, taking a randomized yearly water demand that's been developed by other folks and cited well, I think gives us a pretty robust solution for determining operational costs. And all the different technologies have well, I should caveat that. All the centralized systems have the same water demand requirement. Now, the unitary systems get a 25% reduction in energy demand because they don't have a recirculation loop. So the unitary heat pump water heaters, the electric resistance and the heat pump, yeah, both of those, I think those are the only two on this one, go in with only 75% the requirement at the faucet of hot water than the centralized systems do. Did that answer most of your question, or is there still parts of it hanging?
Yes, you did. I was just thinking like, even when this whole, I don't know how to frame, I'm probably not framing the question right. It's like with the life cycle cost and the operational cost, with the multifamily buildings, how do we work out the logistics? Like, because it's not like a single family home, right? Like one unit, because there are like multiple units. So there could be renters, there could be owners in multifamily buildings. So this was like from an earlier conversation I had with a contractor. So he was also curious, like, how do you work out the logistics when you do the calculation for the life cycle cost and the operation cost?
Okay, well, we treat everyone, I think that's a simple way to say it is, we treat every unit as an individual and simulate what they would need for a year. And then we aggregate that all into one demand by stitching all the uses in time over the full year together. So a single use profile will go to zero a lot, but when you have 100 units, the use profiles that when they overlay on each other, you don't go to zero as often in your drain, if that makes sense.
Yes, it does. Thank you for
Okay.
that.
Yeah.
I had a
The
quick
other
question.
thing.
Oh, sorry. Go ahead.
Oh, the other thing that dramatically impacts it is occupancy level. So if you go to a multifamily unit and they say we only ever keep ourselves at 80% occupied, when we get ready towards pilot, we also have to make changes for that. But go ahead. What was the question?
Oh, thanks. Yeah, for the life cycle energy cost for the unitary heat and water heater versus ER, it looks like that yellow life cycle energy cost is only like 1.5 times greater for the ER, which would imply like a 1.5 COP. That seems super low, right?
Well, in a hot climate, yes.
Because aren't these indoors? You would still be getting I know you were mentioning like taking heat away if you're factoring that in as well, right? But
Yes,
like
yeah.
wouldn't they be indoors still?
Yes, they are indoors, but you're likely heating the space with something like 80% efficient natural gas.
Ah. Oh, so you are
So
factoring that into that life cycle energy cost there.
yeah. So if you're assuming like a COP of 4, 3 units of heat are going to come from the space and one's going to come from your electric resistance. So those 3 units coming from the space have an efficiency of whatever your natural gas is. So that's why in cold climates, and we estimated 8 months of the year, there's a penalty, and the rest of the months there's a positive impact for taking heat from the space because your cooling load is larger. And that
That's a great
changes
point.
a lot by climate location.
Understood. Okay, I think I've looked at some studies where they're often in unconditioned or semi-conditioned spaces like basements where you're
Yep.
not necessarily pulling as much from the like the furnace. And so yeah, super interesting.
Yeah, so unconditioned spaces, you can kind of assume half of the energy of that space isn't coming from the conditions. There's some papers that on it and that are in more detail than what I just said, but yes, in a semi-unconditioned space, you get some free energy as well. But in a multifamily building, likely that heat is going to be coming from the space that you need to be
Yeah,
heating.
great point. Thank you for clarifying that. I appreciate it. And it's really good insight.
Yeah. Trying to think if Minnie's paper has more of these. I think when Yanfi's paper comes out, if I missed any of the details today, you can find them there as well. So Yanfi Lee will be publishing soon on this.
Awesome.
We also wanted to verify the performance of drain heat recovery systems when you would hook them up to a heat pump. So we tested some of these units in the horizontal and vertical. Well, I'm showing the vertical configuration right now. And the good news was for the vertical is when you have sparse flow rate down the drain, which is relatively common even in large multi-family buildings, not all of the uses stack up on top of each other throughout the whole day. You can get pretty good effectiveness out of them. We were shooting for about 75% based on our kind of engineering ballpark calculations of what we needed to make it feasible. And at times we got above that, and at times we got below that. But we've also developed some distributors that increase the effectiveness about 10 to 30%, kind of when you need it. If you look at a distribution of flow rates down a drain, it's way more common to have low flow rates than it is to have high flow rates, although there is more energy available at the high flow rates. So our solution works well for low flow rates, and it pretty much just wets the inside of the pipe better, so you get better heat transfer. The distributors are also coming out in a paper soon. The baseline research was published at Purdue not too long ago, but the distributors are coming next. And then, of course, we had some great colleagues from ORNL that did some life cycle carbon analysis. They used the MISO mix, and there's a lot on that side of what mix to use, but this one's relatively conservative version of what the mix would be. None of the renewables are going to 0%. Or sorry, none of the dirty fuels are going to 0% in this MISO mix prediction of what the grid is going to do over the next 15 years or 30 years. I think this is 30 years was the analysis. And there was some leakage rates assumed within this that we're still debating if they're great ones or not great ones. But I'll try not to get too many details of that today. But the overall picture was that versus natural gas at 80% efficient, that our life cycle energy or our life cycle greenhouse gas emissions would be about 74% lower. So some of these typical water heating solutions are just bar lines, and then you can get into all the different portions of the operational energy CO2 impact versus the transportation versus raw material manufacturing. So ANL has a GREET model that they developed for transportation and then later did for buildings. So now we're just tacking on water heating onto it and having some good discussions with them about what's important for water heating. I thought the wasted water in the recirculation loop would turn out to be a big number on CO2, and it did not. The largest impact is operational energy, and then some of these had R314A in it. Some of them have 513B and A in it as well, which is a pretty big difference when you accidentally leak refrigerant to the air, but typically those were about less than 10%, the leaks for the systems. Any questions on this slide? I hope I didn't muddle it too much. Okay, well,
I just have one very, like, I don't know, I'm not sure if it's the right question, but if there is a refrigerant leak, even if it's less than 10%, does that affect the overall operational cost later on?
So the
And
centralized, the centralized systems, we assumed that every 6 months you'd have somebody come by and check the refrigerant to see if it needed to be charged or not. We didn't factor in an exact value because getting the person out there sometimes is more expensive than the refrigerant to charge it. But it really depends on what refrigerant you're using as well. So that is probably one point that we need to add in is the cost of refrigerant, which we have at this point. But the leak rates are often given in a percentage per year, which makes sense for centralized systems. For the unitary systems, I think the leak rate was really small. I guess maybe only had 3%. But going forward, you can assume those probably don't leak during their use, but when they break, they're just going to get thrown to a landfill somewhere, and somebody's probably going to leak all the refrigerant to the ambient. So the end of life leaks for the unitary systems are likely higher than the centralized systems, because the centralized systems are more likely to have refrigerant tech come out and pull the charge that knows how to do that, and it's going to be a significant charge. So instead of having 2 pounds R134A in 100 units distributed throughout your whole location, you're going to end up with a smaller amount of charge in one location when you're using a centralized system. And generally, the economies of scale suggests that centralized systems make sense for reasons like this as well, which is why I think the majority of the market has centralized systems for their water heating. Because if you look at the big picture, it's less expensive generally. I think I went a little bit farther than I needed to, but thank you for the question. Appreciate it.
Thank you.
All right, so finally to the energy burden analysis, which takes in information about the COP, the location, the water usage, the city water temperature, all of that folds into then what is your operational energy costs. And we ran this result for Minnesota. Now we ran it for Minneapolis, Minnesota, and then we just applied it across the rest of the state because that's the shape factors that GenLi had and was the easy thing to do at the time. But not all these counties have a large portion of multifamily buildings in them. So you really, our next steps are going towards shape files that are for cities only, where we can figure out where the multifamily buildings are, and some of that data is around. We can see at least what cities they're concentrated in. And he's writing a paper about figuring out what cities would be best to go to first based on the energy burden down to as much as fine as detail as there is data out there for. But we applied the energy burden reductions for Minneapolis, Minnesota to the whole state just to see what it would look like. And the relative reductions were about 14 to 42%. I think the absolute reductions in that case are between about 3 to 8%, maybe just a little bit higher than 8%, versus electric resistance. So if you were using electric resistance water heaters in multifamily, this would be the energy burden reduction you'd expect from the drain source heat pump water heater. So I've discussed a little bit of the future work already, but in details, we're looking for a place to pilot this year under ET. And we have a new project that includes space conditioning. I say we, but Renewability is in award negotiations to work with us on including space heating while doing drain source heat recovery as well. So we're pretty excited about that. That's sort of my general update. Is we have another project coming down the way that's going to try to do a little bit more with the drain source heat, this free heat source that all buildings have, that should help heat pumps get out there and a pretty good deal. So we have some older presentations and some published work now, and about 4 or 5 papers in the works. I don't know if I named them all today. One of the other new ones is just going to be a review on water heating in general, residential and commercial. So I want to thank everybody for coming and hanging out, and I hope there's more questions.
Thank you for that, Joe. Yes, we are open for questions and discussions. Alicia is clapping for you. So
thank you.
yeah. So I'm going to just like wrap up few things. So one is that I always had a doubt was about logistics and like how the energy burden is like calculated in multifamily buildings, and how like it will overall affect the operational cost, because then there are like centralized units, and we're not just talking about like one unit, but there are like multiple units in a multifamily building. So even in like cold climates, in a place like Minneapolis, in different regions, depending upon the population density, concentration in multifamily buildings, usage and energy patterns or water usage patterns, all of these factors, even in a minor way, would impact like how much energy is used, and then there is a burden on certain families. So even if there is like this very small amount, like even for maintenance, like even 6 months, would these factors be considered when there is like a pilot study being done, and then these factors would be included in the overall cost calculations?
We do have maintenance costs for the centralized systems of every 6 months having a refrigerant tech come out. I believe it's, if you look at Minnie's paper, you can find the details of that. I believe it's somewhere between $100 to $300 per call. And yes, that does impact what you're doing. You stated that there's multiple water heaters, and that's the unitary description of them. They're supposed to have, not that they always do, but they're supposed to have the energy rod, or sorry, the anode rod checked every 3 years. So somebody's supposed to come out and check and make sure that anode rod is not depleted such that your tank doesn't start leaking. Water heating in general has a very high lack of actual maintenance. There's a lot of deferred maintenance. So one of the things we're trying to do going forward is to figure out, and we don't have a specific project on this. Maybe I'm tipping my hand to the other national labs at this point. What is the impact of deferred maintenance on water heating costs? I'll try not to get into too many details about it, but all technologies, when you defer maintenance, are going to have issues. And they're going to be different for different ones. But to the point you were saying, I'm trying to figure out what is your major concern out of the comment you made.
My major concern is like even if it is like a very minor portion, less than 10% or say 3%, like if there is a maintenance cost or if there is like a probability of error, depending upon the energy use pattern. But when it goes on for for a longer term, it might definitely influence the overall cost calculation, like energy savings or energy
Yeah.
burden or operational cost for that matter. So when there is
Okay.
like, when we do a lab study, there is like a calculator, as you mentioned. The calculator has like, it's based on an approximate number. Like this
Mhm.
is for an average, if this is like 3-bedroom apartment, this is the amount of energy that will be used. But what if there are like, even if there are two people in that 3-bedroom apartment and they have a high energy usage, that might
Yeah.
like sort of infield, that is going to change the calculation. So when there is like, when you're going to come out with a result and you're going to implement it, that time, I think the kind of calculation we have right now with like lower operational cost or the maintenance cost, it might be slightly different given that the real time situations and the energy pattern would influence that calculation, because at that
Yeah.
time the calculator will not be like on a fixed pattern.
Well, yeah. So the calculator we have is randomized, so I wouldn't quite call it fixed, but your point is well taken. And I think it's going to impact sizing more than performance. So if you have somebody in a multifamily complex that uses a ton of hot water all of a sudden, they're probably going to drain the whole system. They're capable of doing that. It is something that does happen. If you go to hot water forum, people scream about it all the time. That you'll have some user who is going to turn their hot water shower on for 4 hours, and it's going to cause a problem. And yes, but it causes a problem to all technologies somewhat equally. I guess you could say unitary, they're going to run out of hot water faster. If you go to apartments that have billable hot water at one source of hot water introduction to the unit, and that's where you're accounting for the water usage, and that's how you determine your bill. You can kind of correct for that one as well. But it's going to impact sizing more, but it's going to impact sizing of all the systems, I would say. Heat pump water heaters probably can handle that a little bit. Well, it depends. It depends, better or worse. Yeah, it's a little tricky. So yeah, it's our best guess going forward, but there's a lot of background research and a lot of papers you can get into if you want to see how we did it and all the things we accounted for. It's been a deep dive on this topic, I think.
That's true. So if there is like a sizing change in the overall unit, does that would that reflect in the first cost again, like when the sizing is also impacted?
Yes.
Like the initial for the unit?
Yeah, I mean, how do I want to? I'm trying to think of the scenario in which you're trying to solve the problem for. Um, Yes, sizing is a problem if you do it wrong. um, and in our case, what we did, and it's a little aggressive actually, or conservative, I should say, is when we were first doing our sizing, and as I'm reviewing our sizing as we go forward, we were trying to replace half of the BTUs of natural gas by tripling the storage. And if you go look at EcoSizer's work, you might not even have to do that. So having an additional heat pump, which is where we're at on one of our projects, and when we were looking at it, when we sized it with EcoSizer, we were double the size on BTUs per hour. So that's one less heat pump that reduces your costs by $40,000 to $50,000, which is really significant. So correctly sizing a centralized heat pump water heater is critical for where the rubber meets the road. But we've been conservative to this point, I would say.
Thank you for that, Joe. Anybody else? Do you have any questions? Noah, Dipti, Alicia, Paul, and Tabitha?
I do. I have a couple of clarifying questions, and if you covered this already, Joe, I'm apologizing in advance. Um, But so you guys have not moved into the field validation portion of this. This is all predicated on existing research and then, your modeling.
Experimental work and modeling, yeah. We haven't gone into field validation yet. It's an ET project. Yeah, we don't always do a lot of field validation, but sometimes it does.
Yeah.
I don't know. I'm getting different feedback from different folks on who does the field work and who doesn't.
Yeah. I'm with PNNL, so yeah, I hear you. It's a fun game. Um, but I would definitely be interested. I mean, I think not that you need my validation, obviously, but I think what you're presenting is a really good a good reason for doing field validation, um, which, is to validate models. So that'll be interesting to see kind of how it progresses. My other question was how your modeling differed for new construction versus retrofit.
So, the initial costs, depending on your viewpoint, will be different for new construction versus retrofit. In retrofit, the centralized distributed system is already there for you. So you don't have to pay to put the copper in and put the insulation on it. We haven't run too much for new construction in the analysis to add that copper cost in yet. It seems significant, but it also has like a 50-year life with some maintenance required, probably 30, 40 years. Yeah, so I don't know exactly the result of including that for new construction yet. We've primarily focused on retrofits for our costs. But the experimental system we're building that's system level is going to be informative for the models as well too. Because then all the components will be together and all the components will be interacting, and that's a lot where sometimes models don't catch everything. So we're excited about that, and we're a little bit higher than the best sewer heat recovery technologies on COP, or at least what I presented today was a little bit higher than the best sewer heat recovery technologies. That's sort of, I don't want to call it a baseline, but it's a location we can also look and we can get data from, and we have from John Heller on sort of verifying our models, since this is not that dissimilar from sewer heat recovery. We just don't store the effluent, we store the heat from the drain. So we're doing the best we can.
Yeah, I mean, there's so many different factors for anything dealing with humans existing. So I mean, accounting for all of them is impossible, but it's super, super interesting. And yeah, I really thank you for your time today.
Yeah, you're welcome. The big forcers are your sources and sinks of energy, and in a cold climate, you just don't have a good source of energy. So we have a pretty big lever arm to play with, I would say, which is why we're not. I feel like when we're out in the field, we'll probably hit similar numbers to sewer waste heat recovery for COP, and we'll probably do better than folks that have they have to macerate their effluent and pump it around a couple times because they end up with a higher pressure system. They end up having to clean their heat exchangers more often than the heat exchangers will have, and they have that pumping power requirement. So I think that's the closest technology to out in the field already to what we're developing.
One last quick question for you. Is this technology, and I'm not as familiar with central systems in general, so just add that caveat, but is this technology sold as like a package solution, or is it kind of a you purchase this part and then this part and you put it together and it creates the system?
The simple answer is it's been put together once by us in the lab, and maybe there's about 4 other papers that have sort of tried it in some scale in the lab as well. So yes, it can be both. The latter makes more sense. If it can be a package system that fits into a location, I know there's a lot of it'll reduce the barrier to it getting out in the field. What I realistically see it being for retrofits is likely more of the kit of parts. You have your tank, you have your water source heat pump, you have the modification you need to do to the drain to get the drain heat recovery in there, and then you're hooking the hoses up between those two, and hopefully it's a kit of parts that's easy enough for folks to be able to move this part to that location where they can fit it. An unpressurized tank outside a building where you just dig a hole, and you don't have to insulate the moderate storage tank for the most part. If you, depending on your climate, maybe you need to put a little bit on it. But if you bury it below the frost line, you don't have to put too much insulation on it. So yeah, kit of parts is probably where it's going to end up. In new construction, yeah, you can probably make it a single install. One company doing the whole thing before the walls go up, all the equipment goes in, and it's not too much of a problem.
Awesome. Thank you.
We still have 5 more minutes. Any questions, anyone? Good to go. So thank you, Joe, for your presentation. I'll just take back the control so that I could move the slide to the last one.
Okay. Oh, I stopped all of us. My bad.
Okay, that's okay. I can do that again. Not a big problem. Just wanted to go back to the last slide and have a closing notes before we wrap up this meeting. Awesome. So you're still looking for the sites for like the field validation in Minneapolis?
We're checking out multiple sites. So what we do is we'll talk to somebody, they'll give us their energy costs, and we'll run the simulation and give them back what their expected operational costs will be based on their gas prices and based on their electricity prices and based on their estimate of how their current system is performing. So we've run it for Syracuse, New York. We've run it for Minnesota. We've ran it for Chicago, Riverside, California. We're building up a pretty large network of solutions. We just need to find the folks that are willing to let us put it in our field site, and we're hoping we're going to get a new water-to-water heat pump donated by a major manufacturer here soon, such that it's going to reduce the cost as well for our pilot.
Hopefully that will work out soon. And do keep us posted when it goes onto the field.
Will do. Thank you.
Sure. Thank you, Joe. So just closing up, thank you for joining us for the meeting today. And in case you have missed out on the heat pump water heater day, you could catch up some of the videos and recordings and sessions on the panels on the YouTube channel. So I've just added a link where Maggie and Dipti were in the panel, and they had a discussion on the roadmap to the future transformation 2040. Also, in case you missed out the webinar on clean energy workforce diversity, which was conducted last month, and so, two of our working group members, Monica Guerra and Sandy Fisher-Lobby, were the panelists, and they had some really incredible, insightful discussion on the workforce diversity. So if you'd like to catch up on that, you can also do that. It's up on the YouTube channel on AWHI page. You can check it out. The link is added to the slide. Also, the next meeting is tentatively, for now, decided to be on 18th December, but I'll keep you posted in case there's a change of plan. So that will be all from my side. Thank you so much for joining. I wish you all a great rest of your day. Have a good time. Thank you, everyone.
Thank you all.
Thank you.
Bye-bye.
Thank you so much. Have a
Thank
good
you.
night.
Yeah, good night.
Bye.
Bye-bye.